All right, so here's class 19, and we're continuing with chapter 5, and this is going to be the inequality of Clausius. Let's see what he's all about. So here you go, the inequality of Clausius, and according to Wikipedia, the Clausius statement states that it is impossible to construct a device whose sole effect is the transfer of heat from a cool reservoir to a hot reservoir. All right. So basically it's saying in order to have a refrigerator, you need to you need to put some work in. So there's no way that you can get this accomplished. So we've already had that kind of statement with Clausius, but let's turn it into something that we're going to use in the next chapter. So spoiler alert, once again, I said it too much, don't I? That we are going to do something called get something we refer to as entropy, and this is sort of like the introduction to entropy. So we talk about the cyclic integral, just saying that we're going to keep going around and around and around, and so that the net heat transfer has to be greater than 0, right? So we're always going to be losing something, and so we have this little statement right here that if it was a reversible heat engine, the set of circumstances that we have is when dividing the change in heat around the cycle, right? So we get the little circle right there. I mean, going round and round and round and round, back and forth to the thing. So you can see right here, here's the back and forth around the thing. It's going to be equal to 0 for a reversible. But for an irreversible cycle, it's got to be greater than 0. So here is really the inequality across Clausius. It's going to end up being a negative value right here. So let's just go ahead and show it instead of trying to derive it. I think it's kind of better anyway, just to try to believe it. So we're going to walk through this real cycle. And we made the only kind of concessions to maybe not so real is that somehow we are saturated vapor here coming out of the boiler. We're saturated liquid and they're at the same pressure. So the pump has somehow taken this 10% quality and moving it up to there. That's not really kind of real, but that's okay. We can go ahead and work through there. So we will look up what all these properties are and then do an analysis where we apply this idea. That's our goal. That's what we're doing. So let's take a look at this and print it in color this time. So here is, and of course we can look these up one at a time. But let's just go ahead and take my word for it with these properties right here. So, but first thing, this is a saturated vapor. So one thing we'll know is that T, I labeled them wrong here for some reason, and I will fix it on my sheet. Although it's probably kind of right in. I guess it's semi-correct. Now I'll go T2, right? So anyway, this is state 2. And it is a saturated vapor at 700 kilopascals. That's going to be 165 degrees Celsius. I'll just round down. And we're going to have an H, and so this is the Hg, if you will, at that state, is going to be 2,764. These are kilojoules per kilogram. Coming down over to here, we get 90% quality at 15 kilopascals. So we can get at this pressure, the temperature, saturated temperature, T3, is going to be 54 degrees Celsius. And H3 is going to be 2,362 kilojoules per kilogram at that quality, 90% quality. Over here, now we're at 15 kilopascals. It's the same right here, so it's actually the same temperature. So this is a isothermal across there, but now we have so here 54 degrees Celsius, but we have removed the latent heat of vaporization and almost the entirety, so it's still kind of steamy. That's kind of tough, right? So it's still 10% quality of steam. Pumps don't like that. but somehow we're magically able to do it. So, so using that 10% quality, we've been able to get the thing down to 463 kilojoules per kilogram. And then back up here at the pump, we are a saturated liquid, so we're saturated at 700 kilopascals again, which means we're also at 165. So that'd be T1 is 165 degrees Celsius as well. And but the I'm going to go H1. I'll put it up here instead of where the pump inlet. Let's go to the pump outlet. It's going to be 697 kilojoules per kilogram. So that's going to be the HF at 0.7. All right, so I think we get everything. So let's. The only two places where this heat exchanged, right? And remember that we're looking back at the Clausius inequality thing. Right? We're looking at this guy. We want to see if this is true. So let's add up. In order to write this out, let's go here. Is del Q over T. That means we're going to add up and make sure that we go ahead and treat things like that are negative as if they're negative. And let's do it on a small q basis. I'm trying to figure out how to do this, or how to rewrite the thing. Yeah, I think I'm okay. Yeah, I'll just rewrite the thing out here. That we have the del Q over T of the boiler. And I guess we'll do it this way. It's the signs that I'm pausing over. And I call the BLR for the condenser, for the boiler, and CND for the condenser. All right. And the temperature is constant across both of these, so we could just go ahead and do the integral of the thing and go 1 over T 1, because the temperature 1 is 165 and 165 across the thing. And that's going to go integral del Q from 1 to 2, and then plus T over T3, because this is temperature 3, remains the same here as right there, right, 54, 54, and integral del Q going from 3 to 4. Right, so the only two places where heat is actually exchanged. It's not exchanged in the pump, not exchanged in the turbine. We can say that treat those as if they're adiabatic. And okay, so what we end up with once we integrate these things is going to be Q 1 to 2 over T1 plus Q 3 to 4 over T3, right? So that's the test that we're going to play. Now, we don't have a mass flow, so we can use little q's instead. So we go Q 1 to 2. It's going to be equal to H2 minus H1. No masses, but this is a steady flow situation. Looking at, we're just isolating the boiler right here. So there's the mass flow in and mass flow out. Mass flow is the same everywhere, so we'll just do everything on a mass flow basis. And that's going to end up being 2,764 minus, so that's the yeah, this is coming out, right? So this is out of the boiler up here, and here is coming in, and this is 697. So we have a 2,067 kilojoules per kilogram. And then the Q 3 to 4, let's go H4 minus H3. So we get 463. That's for this guy coming right out of the condenser. Minus what's coming into the condenser, 2362. It ends up being negative. And that negative really is, you got to be careful with these signs, whether you're going to base the signs off, which order in which to do things, or just not based on you know that it's going to be heat rejection to make that negative. So that's going to be what we place up back up here. So I'll rewrite this a little bit different. Here's our there's our del of the statement of Clausius right here. So we will go the Q1 to 2 over T1 plus Q3 to 4 over T3. And so that's 2067. Now T1, you got to remember to make this into, it's very important, make it into our Kelvin, absolute temperature. So this is, T1 is 165 plus 273. And this is plus negative 1899. And so this temperature is going to be 54 plus 273. And what we end up finding is we had a negative 1.088 kilojoules per kilogram degree Kelvin. And so, therefore, this is less than 0 and satisfies Clausius. Inequality and equality. Yeah, got an I right there. Something to note. Before we divided it by that temperature, this was going to be a positive value, right? So it does matter that the temperatures underneath it. And also, these values wouldn't be correct if we hadn't made them absolute. So there's a couple things to be on the lookout for if you're asked, and I haven't asked you in a homework to do it, but maybe you're asked some other point, maybe on an exam, I don't know. You can look it up, try to figure it out. Does this cycle satisfy the inequality Clausius? Well, you want to go through this mindset. So this is a good problem for that, but I didn't ask any on the homework, so just be aware. I'm going to make another video for the next one, for the next example. So I got several in here, probably too many, but we'll see. Goodbye.